Hey there guys, Paul here from theengineeringmindset.com. In this video we are going to be looking at the heat pump VRF unit, which can provide heating or cooling, but not simultaneously. Now this video follows a series on the subject of VRF systems, so if you haven't done so already, I highly recommend you go back to the beginning of this series to build up your base knowledge before moving on to these more technical versions. Now the heat pump VRF unit is the next step up from a basic cooling only VRF system, and this is because a heat pump VRF can provide heating or cooling, but remember it cannot provide both at the same time. So looking at the simplified schematic here, it's very similar to a cooling only system with the outdoor unit and the indoor units. Outdoor units here and the indoor units here. Again, you don't have to have these ceiling cassettes. It can be a fan coil unit or an AHU, etc. But for simplicity, I'm just going to leave it as these cassettes. Now it also has just a two-pipe system with the flow and return come along, feeding into the internal, the indoor heat exchanger, and then returning back to the outdoor unit. Now notice I don't refer to these as a condenser and evaporator as you would with a standard split AC unit, and this is because as it's a heat pump unit and it can provide heating or cooling, the role of these two are actually reversed. So in cooling mode, then this will be the condenser and this will be the evaporator, as you would expect in a normal split AC unit. But in the heating mode, then the indoor units actually become the condensers and the external unit actually becomes the evaporator. And we'll start to look into this later into this video, what the difference is and how that works. Now, like I've mentioned a couple of times now, the heat pump can only provide heating or cooling, but it cannot provide this at the same time. All units on that system will have to provide the same heating or cooling, and I'm going to represent this by this white line splitting between heating or cooling. As I said, some can be off and some can be on, and that will not affect the rest of the system. They will all either provide heating or cooling. Now as we look internally at the kind of internal schematic of what's happening here in the heat pump, you can see this is currently in the cooling mode, and the refrigerant is leaving the compressor, and it's leaving the compressor as a high pressure, high temperature, superheated vapor, just like any other refrigeration cycle. Now before it reaches the heat exchanger, which is at the moment acting as a condenser, before it reaches there, it passes through a 4 port reversing valve. Now with the reversing valve, there's only one inlet, and main inlet anyway, and there is 4 kind of outlets here, and this U-bend here, this can change position, so it can either channel the flow between these two pipes, or it can shift over and provide it through these two pipes here, whereas the incoming from the compressor will either go straight over into the heat exchanger, the external heat exchanger, or it will divert when this moves over and head directly here to go into the indoor units and the indoor heat exchangers. But at the moment, so this is leaving the compressor and heading through the reversing valve, and it's in cooling mode, so it's going to head over to the external heat exchanger, which, as I said, is acting at the moment as a condenser. Again, we've got a fan in the top of the unit here, which is sucking ambient air into the unit and blowing that across the heat exchanger and pushing that air then out of the top of the unit. So as that air flows over the heat exchanger, it picks up some of this unwanted heat and rejects that out to atmosphere, cooling that refrigerant down. As the refrigerant leaves that condenser, it's going to be leaving as a high pressure, medium temperature, saturated liquid. Now the next stage past this external heat exchanger and condenser is the check valve and expansion valve. Now because it's operating in cooling mode, we do not want to expand the refrigerant just yet. we want to bypass that, so we go through the check valve. The check valve just allows the refrigerant to flow in one direction. It will stop it flowing back in this direction when it's flowing this way, and it would then in turn, when we'll see that, it will go through the expansion valve instead. So in this setup, it's going to bypass and go through the check valve, bypass the expansion valve, and head along through this common pipework over towards the indoor units, which are currently in cooling mode. Now once it reaches the indoor units, you can see here there's another setup where we've got the check valve and the expansion valve. Now in this scenario, because it's in cooling, so we want to expand it, so the refrigerant is blocked from entering this way, as there's a one direction only valve, a check valve, and so the refrigerant then passes through the expansion valve, and that then enters into the indoor unit, which then provides the cooling effect. So when the refrigerant hits the expansion valve, it's going to be in this part here, it's going to be a high pressure, medium temperature saturated liquid, and once it leaves the expansion valve, it's going to be a low pressure, low temperature liquid vapor mixture. This refrigerant is then going to make its way around the heat exchanger inside the indoor unit. Remember, it's a ceiling cassette, and as it does that, it's going to give up its heat, because the fan inside the cassette is going to be pulling warm air from it within the room across the coils, and the coil is then obviously cooler because of the refrigerant that's inside it, and that creates a heat exchange. Remember, the refrigerant stays inside the pipework, it does not leave and enter the air. That would kill everyone if you did that, so make sure that doesn't occur. So as the air leaves, it leaves much cooler and then pushes that back into the room to recycle that air and bring more warm air back into the cassette. So by the time the refrigerant leaves that cassette in the cooling mode, it's going to be leaving at a low pressure, low temperature saturated vapor, and the force of this refrigerant, which is constantly being pushed around, that is going to be forcing that refrigerant back round again into the reversing valve, through the U-bend and straight back down into the compressor. Well, it will repeat the cycle again and again and again until the entire system is turned off. Remember, the electronic expansion valve is constantly taking measurements on the other side of the cooling coil, and that is making very small adjustments to its position, allowing more or less refrigerant to flow into this system, and as it restricts the flow, that builds up pressure in this pipe here, which is where the controls of the variable speed scroll compressor comes in, and that is where your energy savings come in. And we're obviously going to look at that, but in much more detail in the controls video later on. Now, the other way the heat pump VRF can work is going into the heating mode, as you can see on the screen now. So with this, it's working basically in reverse. So all the indoor units are becoming the condensers, and all the external unit is the evaporator. So as normal, the high pressure, high temperature, superheated vapor leaves the scroll compressor, and that heads off up to the reversing valve. You can see now that the reversing valve has now reversed, and so now that refrigerant will flow directly through this common pipe and off to each of the internal heat exchangers, the internal units, which are now acting as the condenser. So that unwanted heat, which was, if you remember in the cooling mode here, is rejected to the outside. In this setup, it is sent back indoors, and it is then pushed out, so the fan is then bringing the cooler air from the room and blowing that across the heat exchanger, the coil, and that refrigerant, because it's hot, is obviously exchanging some of its heat over into the air, and so that then passes through there, and that refrigerant will then start to condense as it passes through this. So by the time it leaves and heads through this check valve, remember the check valve just ensures the refrigerant is flowing one way. So by the time it is reaching this common pipework here, that should be as a high pressure, medium temperature, saturated liquid. So all of these units will push out their the liquid if they're on. If they're not, then obviously there will be no refrigerant flowing into these, but the fan can still be in use, so air can still be blowing across even though there's no refrigerant flowing in these units. And but anyway, coming back, the refrigerant enters into this pipe, the common pipework, and that heads back to the outdoor unit. When it reaches the outdoor unit, it will then head and go through the expansion valve here. If you remember, on the cooling mode, the refrigerant is passing through the bypass, going around the expansion valve, but in the heating mode like this, it's going through the expansion valve. So as the expansion valve, as the refrigerant passes through there, so it's entering the expansion valve as a high pressure, medium temperature saturated liquid, and it leaves the expansion valve as a low pressure, low temperature liquid vapor mix. It then enters into the external heat exchanger, which at the moment is acting as an evaporator, and that is then absorbing thermal energy from the ambient outside air. So within the air there's going to be small particles of thermal energy, and it depends on how much there is by obviously the temperature of the air. And while this is acting as an evaporator, it's picking that thermal energy up and is pushing that then through into the reversing valve and down into the compressor, where obviously the cycle will then repeat and reject that heat. And like I said, this evaporator is then pulling thermal energy out of the external air. There is always going to be thermal energy in the air. It doesn't matter how cold the air gets. In fact, the external air has to be below minus 273 degrees Celsius or 523 degrees Fahrenheit for there to be no thermal energy in the air. So we can safely operate without above these limits. So even in the winter, you'll be able to take thermal energy out of the air and push that into the building. That is how a heat pump works. Alright, that's it for this video. Thank you very much for watching. I hope you've enjoyed this and it's cleared up some doubts you had. Please feel free to leave some comments in the comment section below, and also like, subscribe and share. Once again, thank you very much for watching.